Hello. In this lesson, I'm going to explain integration. The first thing you need to know about integration, especially with the symbology, is that when you see this notation here, shown here on the left, it is read as the integral from a to b of the function f of x dx. The function is called the integrand, and the a and the b are the bounds. And the thing you want to know about this is this represents area between the x-axis and the graph of the function f of x between the bounds a and b. So when you see something that looks like this, integral a to b f of x dx, it represents the area which I've shaded here uh, below the function f of x, above the x-axis, between the bounds a to b. That's all it means. It means area. Now, if we can use straight lines, we don't need to get fancy. We can use geometry, as I'll do in a moment. But where calculus comes in handy with integration is for shapes that aren't straight lines, for example, curves. And that's precisely why we need calculus. Why is area important? Area represents the accumulation of a quantity. For example, if the graph is a rate function, the area below the graph is a total accumulation function. For example, let's say Sue jogs 8 miles per hour. That is a constant rate. So her graph, which I've labeled v of t to represent velocity, is just simply equal to the number 8. It is a horizontal line 8 units above the t-axis in this case. For every hour that Sue jogs, she accumulates miles in this case. So after 1 hour, she has jogged 8 miles. If she jogs for another hour, so between 1 and 2, that's another 8 miles. So for every hour she's jogging, she's accumulating another 8 miles. She's going to run a marathon here, it looks like. Now, in this case, I can represent this as the integral from 0 to 1 of the integrand 8 dt, since I'm using the t variable here. This little guy in the middle would be the integral from 1 to 2, 8 dt. And the third one here would be integral from 2 to 3, 8 dt. Now, if I would take them all together, in other words, I look at the whole area here, the integral from 0 to 3 of the integrand 8 dt. But we don't need to get that fancy here. What shape is this? These are rectangles. We just use the area formula for a rectangle. So for example, the total miles that Sue jogs during a 3-hour period would be represented by a rectangle that you can see here, this rectangle that I'm kind of outlining. It's got a base of 3 and a height of 8, and we just multiply that. Just use the formula for area of a rectangle, 24 miles. Okay, let's look at another example. Larry earns $15 an hour at his job. So he's accumulating money for every hour that he works. So in the first hour, from 0 to 1, that's represented by a rectangle. And I'll label that here as an integral from 0 to 1, 15. And again, I'm using letter t for the variable. And I can actually represent that he's made $15 in that hour total. He's accumulated $15. So let's jump to the natural question. What if I want to know the integral from 0 to 8 of 15 dt? Okay. Now, again, I don't want to actually perform an antiderivative. I want to use geometry here. So I'm going to draw a line here at 8, and I'm going from 0, which is over here on the left. I'm looking at the whole area, everything here you see. How much money has he accumulated? Well, again, I look at the shape, it's a rectangle. The base is 8. The height is 15. If I multiply that together, I get 120. So if he works 8 hours and he's making $15 per hour, he's going to accumulate $120. The area that you see here is the amount of money he's accumulated. So the area is actually representing a physical quantity. Okay. So let's look at a case where the rate function is not horizontal, so we can't use rectangles. Chris is riding his scooter at 30 feet per second. He brakes, slowing linearly to a stop after 10 seconds. How far did he travel in those 10 seconds? Well, I have a graph here. It starts at 30 feet per second, so that at the moment he starts the braking, we'll call that time 0. And then 10 seconds later, his velocity is actually at 0. So 0 on the y-axis, okay? So I want to know, how far did he travel? Well, the distance is going to be given by the area. Now, technically, it would be an integral from 0 to 10 of this rate function. I'll just write Chris's rate function right here. Oops, there you go. dt. Okay, I'm not gonna even bother trying to figure out what that function actually is. All I need to know is there it is. It's a line that goes from 30 on the y-axis to 10 on the t-axis. But the thing is that the area in here is the distance he's traveled. If I can find that, I have my answer. I don't actually need to perform any calculus. This shape is a triangle. The area formula for a triangle is 1/2 base times height. I just look at my picture. The base is 10. The height is 30. And I just work out the math. It's going to be 5 times 30 or whatever. You get 150. And we can assume that during those 10 seconds that he was braking, he actually traveled 150 feet. So from the moment he hit the brakes to the moment he stopped, he covered 150 feet. So to summarize here, in a sense, Chris is accumulating distance. Even though he's braking and he's slowing, he's still accumulating distance. And from a calculus standpoint, I can graph his rate function, which you see here, and I know that the area is going to be useful to me. It's actually the distance in this case. I just need some way to find it. If everything in the world was straight lines, we wouldn't need calculus, all right? We could always just use geometrical formulas. In this case, I went ahead and just did that, 1/2 base times height, okay? So this is a case where, again, it's a calculus concept, but it was solved just using geometry. So let's review a couple of the common geometrical formulas for area that we have. For rectangles, area is length times width, or base times height, same thing. Triangle, the area is 1/2 base times height. And a circle, a full circle, area would be pi times radius squared. Okay, so of course, we'll adjust that as necessary. So let's look at this picture right here. Let's call this crazy looking function, let's call it g of x. G of x is this oddball looking thing. Suppose I want to know the integral from -1 to 0, g of x dx. Again, you look at that, don't look at that as something mysterious. Just say to yourself, area, A-R-E-A. That's what that means, area. Okay. So what it's asking is that, what's the area of this little triangle back here? Okay, here's -1 and then here's 0. Well, I can just look at it. It's 1/2. Base is 1 unit in length. Height is 2. So I just went up here to 2. And I get 1, frankly. So the answer to that question is 1. Okay. What if I do the integral from 0 to 1 g of x dx? Well, now I'm looking at this little bit right here. Here's 0, here's 1. I'll draw a little line to go up to it. This little region here then is a rectangle, and I just use the base is 1, and the height is 2. So 1 times 2 is 2. Okay. Let's do from 1 to 2. Integral from 1 to 2 of g of x dx. So there's 2, 1 to 2. That's a triangle. The area formula for a triangle is 1/2 base height. So the base is 1. And the height is 2 again. So we get 1. 1/2 times 1 times 2 is 1. And then let's do it for this little bit down here, this little circular bit. So from 2 to 4. So here's 2, here's 3, here's 4. Well, it's actually a half circle. The radius is 1. Remember, the radius is the distance from the center to the circle itself. So I can draw a line here, for example, that's 1. Okay. So I take the formula up here, pi r squared, but I have to multiply it by a half because it's half a circle. It's a half times pi times 1 squared, which is pi halves. It's about 1.57. Okay. But here's the thing. It's below the x-axis. So it's negative. So any area that's below the x-axis is negative. So I'll say area is equal to negative 1.57. Okay. So let's bring this one on home. Let's get the grand finale. How about the integral from -1 to 4 g of x dx? Now I did them all in little bits. I did from -1 to 0, 0 to 1, 1 to 2, 2 to 4. The whole integral from -1 all the way here to 4 will just be the sum of all the little bits we figured out here. 1 plus 2 plus 1, take away 1.57. So that comes out to 4, take away 1.57, which is about 2.43. And that's the net area. Okay. Remember, if it's above the x-axis, it's positive area. If it's below, it's negative area. All right, let's look at another example. Here I've drawn a picture. It's a function f of x equals 2x. I've labeled 1 here, and then I've labeled b here. And the question is, what's b? What's the bound b such that when I integrate from 1 to b of this function, I get 14? Okay. Well, I can do this a couple of ways. I'm going to go ahead and write it using the actual integrand, which is 2x. And I could use geometry because if I draw B and I go up here, this actually forms a trapezoid, but that can be decomposed into rectangles and triangles. But I'm going to go ahead and jump into the antiderivative approach too, okay? Because you do have to know this. So when you're finding area under a curve or any function, if you know what the function is, go ahead and pop it in here into the integrand spot, and then just work out the antiderivative. The antiderivative will be, well, I'll do it for you. It's going to be 2 times 1/2 x to the 2. So you add 1 to the exponent, and you divide by the new exponent. But notice that those 2's cancel, so you just get x squared. And then you put the bounds on. And the usual notation is to put a bracket like that. So you put the top bound in b squared minus then the bottom bound in 1 squared. Now that's all supposed to equal 14. Remember that 14 was just kind of given. Okay. So if I just work out the math, it's b squared minus 1 is 14. That means b squared is 15. And that means b is going to be square root 15. Now, I don't take the negative square root because I want to be to the right of 1, and square root of 15 is approximately, doing on my calculator, it's about 3.873. That would be the top bound that if I plugged it in here, so if I integrate from 1 to 3.873 of this function, I should get 14. All right. Let's look at a couple of cases where the functions themselves are curves. This is where calculus really comes into play. So we use antiderivatives to find the area if geometry alone is not sufficient. Okay, so in this case here, the first case, I have the function y equals x squared, it's a little parabola. And I want to find the area between the curve and the x-axis between the bounds 0 and 4. That would be represented by the integral 0 to 4 x squared dx. All right. The antiderivative of x squared, you do the power rule, which is you add 1 to the exponent, and then you divide by that new exponent. I put that bracket there with the 4 and the 0. I put the 4 in to the x, and then I put the 0 in to the x, and I subtract. Now 4 cubed is 64. 0 is just 0 cubed is 0. And I have, remember, the 3 on the bottom. So actually this one just works out to be 64 thirds. And as a rough approximation, 64 thirds is 21 and 1/3. That would be units, square units. I'm sorry about that. Let's look at another case here. I chose a function here that's partially above and partially below the x-axis. The function is y equals 2 square root x minus x. I'm going to shade in the area here. Notice that some of it's above the x-axis, some of it's below. Let's see what happens. I want to integrate, let's say, from 0 to 10. All right, both of these terms, the power rule applies. Let's do it right here. For the radical, remember it's 2. Let me write it just real temporarily as the 1/2 power. So I haven't integrated yet. Now I'm going to integrate. The 2 is just, the front 2 is just a going along for the ride. So I add 1 to 1/2 and I get 3/2. And then I'm going to divide by 3/2, but that's the same as multiplying by 2/3. Okay, so let me verbalize that again. You add 1 to the power and you get 3/2. When you divide by 3/2, that's the same as multiplying by the reciprocal 2/3. The negative x is just going to be negative x squared over 2. Add 1 to 1, you get 2. Then you divide by that 2. All right, let's clean this up just a tad. It's going to be 4 over 3, x to the 3/2 minus x squared over 2. And I'm going to put the bounds on 10 and 0. I plug in the 10. And then when I plug in the 0, notice that I'm just going to get 0 both times. So I'll just write a single 0 there. That's just going to drop out. So I get a crazy answer here. I'm going to need a calculator for that. So 10 to the 3/2 power is about 31.623. Now that's 10 squared is 100. So 100 over 2 is 50. And of course, that just doesn't need to be written at all because it's 0. So if I finally work this out, so 4/3 times 31.623 and then minus 50, I actually get a negative number. I get negative 7.836. Okay. Now remember, when you have a case where the curve is both above and below the x-axis, like you see here, this is going to give you net area. And the fact that it's negative indicates more area is below the x-axis than above the x-axis, okay? Well, so I want to thank you for joining me for these 10 or 15 minutes, and I hope that this little discussion on integration has helped you. If you practice these and become good at it, you too can be a pirate of integration. Keep up the good work.